Okay, so welcome you to the live session of this particular NPTEL course, Technologies for Clean and Renewable Energy Production. This is the seventh live session is being conducted on 10th of September. So what we do in this live session is get a brief overview of this particular what has been taught in the last week and followed by some sample question answers. So in this week, the first lecture constituted the overall things about the hydropower. So it consisted of the following points such as hydrologic cycle as a renewable energy source, mechanism of hydroenergy production, components of hydropower plants and their role, classification of hydropower scheme, advantages and disadvantages of hydropower in India and world. So if we see uh, the first lecture, the overall basic hydrologic cycle and hydropower has been discussed. Is nothing but a overall cycle where the precipitation happens by rains and all, and then it flows via the stored in dam, and then flows via rivers, and then flows into ocean. Then it also, and the overall things get evaporated by with time, and then again it gets accumulated in the form of cloud. And then again the clouds cool, cause precipitation, and this is the overall cycle. And the overall mechanism by which hydroenergy is produced is also being taught, and based on some mathematical formula, such as the basic equation of power, if you know, is power is a multiplication of discharge, head, overall efficiency and density. Okay, so it can be expressed in this way, like eta rho g q h. So if we put the value of G, it will be like 9.81 eta QH, and based on that, an energy generated can also be computed from here. It will be nothing but time multiplied by power. So based on that, one kind of problem is also discussed here. A mountain stream flows over a terrain where micro hydropower plant is possible, where an effective head of 50 meter be built and a flow rate of 0.6 meter cube per second can be maintained. How much power can the hydro plant generate? Assume plant efficiency of 83%. Certain values are provided here, right? So the head is 50 meters, Q is 0.6 meter cube per second, the eta is 83%, means 0.83. You just simply multiply them with G, 9.81 eta QH. So multiply all of them, we get the power 244 kilowatts. And from that, how much energy will the hydro plant generate each year? So each year it's provided, so 365 days multiplied by 24 hours per day, so 244 kilowatt or 0.244 megawatt into 24 into 365, it will be like the overall energy generated. Okay, another additional component is that what is the number of population that can be supported by this energy. There is a per capita electricity consumption in India is given here, about 780 kilowatt hour annually. So you just need to divide the overall energy generated by the per capita energy consumption 780, will get the population which can be supported by this particular power plant. Further components of the hydropower plant, such as the civil works, hydromechanical equipment, electrical equipments, all these are provided. Classification of hydropower, generation based, head based. So generation based, it can be divided from less generation, like from picowatt, microwatt, mini, small, these kind of things. So micro, mini, it is the range of the kilowatts. And from small power plant, it means it goes from the megawatts, and the large power plant, it means that more than 100 megawatt. Head based also can be classified like a ultra low head. It means that it's below 3 meter head, and a high head is can be as high as 75 meter and above. The classification of hydropower, it can be based on, again based on purpose, classification based on hydraulic features, classification based on basis of operation. Classification based on purpose means the single purpose project or multi-purpose project, which means that along with the power generation there can be multiple purposes such as irrigation, drinking water, all this. Or single purpose project means only power generation. Okay, the based on hydraulic features, it means that Sorry. Based on hydraulic features means that conventional hydropower plants, such as it consists of the utilization of available hydraulic energy of the flowing water. All the existing plants are of this category in India. Okay, so the conventional one is utilization of the available energy of the flowing water. The pumped storage plants, which means that there is a certain storage and then it would be certainly recycled. Okay, and then there is the tidal. Based on the tidal waves, it is a certain waves or tides are there, and based on that, whenever these tides come, it the power plants work. Apart from that, the basis of operation, it can also be classified as an isolated plant, which means that it is not connected to the grid system and directly meets the demand. Okay, such as whatever demand is that only that amount of generation would be there. That's it. And if it's a grid connected plant, which means that the excess energy would be fed into grid, and in this form it can be basically stored or something. Okay, further hydropower schemes are also be discussed, such as run of river, it is based on in the river bed or by diverting river, canal fall base in the existing canals, storage dam. Pumped storage has two reservoirs, as I told earlier. It and the water can be stored in the form of a particular reservoir. Okay, so these are certain examples of run of river. Like the particular thing is based on a river area. The canal, if is a canal, is basically diversion from a river. So based on this canal, the powerhouse is constituted, and the entire uh, generation plant is formed. Okay, certain such as such examples are also shown here. And then a storage dam base, in the dam it is basically stored, and then whatever water has been released from it, the the powerhouse is generated there, and there is certain grid and all this, the whatever energy is generated, it can be supplied to the grid also. Okay, so you can see in the this dam based things. A dam is basically a dominant feature. Powerhouse is at the toe of the dam. No diversion of water away from the main river is involved. Okay, so these are overall different types of power plants has been discussed, and overall the advantages and disadvantages uh, are here. Like the advantages involved are basically overall a green and renewable energy resource, such as emission free with virtually basically no NOx, SOx emission, hydrocarbon particulate emission can be there in this particular thing, the hydropower plants. Okay. Mhm. It can be easily dispatchable with a certain storage capacity, and based on the demand and possibility, uh, these can be certainly like scaled, like upscaled or downscaled easily. So from 10 kilowatt to 20,000 megawatt, it can this can be varied. Some of the examples are also shown here. like worldwide and in India also. In this line, the lecture 2 consisted of the hydromechanical equipment like turbines, impulse turbines, reaction turbines are different components of turbines, specific speed of turbines, selection of turbines, turbine generator unit, component of a generator, types of a generator, types of gates, like that. In this particular lecture, what had been taught is different hydromechanical equipments, such as a turbine is a very important thing. In that, different types of turbine like reaction turbine or impulse turbine is there. And overall, a water turbine is nothing but a rotatory machine that takes the energy from the moving water. Flowing water is directed on the blades of a turbine runner, creating a force on the blades. Since the runner is spinning, the force acts through a distance, and this way the energy transferred from the water flow to the turbine. The turbine turns a metal shaft in an electric generator which produces electricity. The principal types of turbines are such as this is the different types which are showed here. Among that, there are impulse turbines, uh, Pelton turbines, Cargo turbine, like that. Different examples of that. You have to read it in this particular PPT what lecture notes which will be shared with you, which are I think already shared with you. Okay. After that, there is a reaction turbines. The examples of reaction turbines are Kaplan turbine and Francis turbine. There is propeller type turbines, and all these different types. I'm not going into details. Okay. Now the selection of turbine type is also very important. You can see depending on the flow, depending on the head available, you need to select the turbine. Okay, then these particular boxes show the area or the region of selection. Okay, for a low flow and low head, you need to choose a Kaplan turbine. For a comparatively larger area, larger region, Francis turbines can be chosen. So you need to get that whatever head or whatever flow is need to give to the turbine. According to that, need to identify in this particular plot and see what is the particular turbine which will be most suitable for our system. Okay, for a higher head, low flow, the turbo turbine would be nice. For uh, further, greater head and still, up to about 60-70 meter cube per second flow rate, Pelton turbines will be good. But for both a very high head and high flow, like when you try to get to the 1000 megawatt power generation, then uh, Okay, so there are different components of turbine like penstock, like spiral casing, guide vanes, runner, draft tube. All these different mechanisms accordingly is guided of a particular turbine. There are also different components of generators. Main generator components include stator, rotor, upper bracket, lower bracket, like that. Okay. And based on that, the power generation calculation can be done. A standard equation for calculation of the energy production, it can be done via the multiplication of head, flow and efficiency and divided by 11.8. Okay. Such example is also shown, like there's a dam which is 357 feet high. The head, which means the distance the water falls from, is 235 feet. The typical flow rate is 20 to 100 CFS, and we are assuming that it runs with about 80% efficiency. So if you see, the power generated is about 235 multiplied by 2200 multiplied by zero point 0.8 and whole divided by 11.8. So about 35,051 kilowatts, like that. Okay. And overall efficiency hydropower plant depend on the individual efficiency of these particular components. So it would be again multiplied by the efficiencies of these different components. Okay, so efficiency of turbine multiplied by generator multiplied by gearbox, like that. So turbine having maybe efficiency of 88 to 94%, generator 96 to 98, gearbox 98%. So need to just multiply all these efficiencies and then get the overall efficiency of a hydropower plant. Overall it comes around 75%. And there are different types of gates also for hydropower, such as a radial gate, which opens and closes like this in the vertical direction. The slide gate is nothing but a sliding door, maybe in vertical or horizontal direction, and also might be a circular gate, so it acts in a circular way. So the third lecture consists about geothermal energy. The geothermal energy is a source of renewable energy, application routes of geothermal energy, mechanism of conversion of geothermal energy to electricity. Okay, then different types of electricity production plants, advantages and disadvantages, world scenario, Indian scenario, and some numerical problem. Okay, so geothermal energy as a renewable energy source is discussed. Different application routes of geothermal energy, such as direct or indirect exploitation of geothermal energy, and again the direct use of geothermal energy in residence. An overall mechanism for electricity production via geothermal energy is also discussed. Okay, and the different options for electricity generation via powered steam power plants like dry steam power plant, flash steam power plant, binary cycle power plant. These things are discussed. And overall, then again, the advantages and disadvantages of geothermal energy, such as the advantages incorporate the renewable and sustainability of this particular type of energy, is a cost effectiveness, a constant supply, environmentally friendly, small footprint, low noise, low maintenance, huge potential, job creation, all these things. However, the disadvantage of geothermal energy greatly dominate over the disadvantages. Okay, so majorly the disadvantages such as the geographical limitations, large investment are required, environmental impact, sustainability concerns, and seismic instability, because it is actually generated via the through the Earth's crust and is kind of a fossil type of energy. Okay, we'll be discussing further in the questions also. And the final one is about the tidal and wave energies. Okay, yeah, I'll come to that. I'll come to that. Uh, Environmental impact. Yeah. Okay. So the final lecture, it constituted about the waves and tides as a source of renewable energy. Okay. The major constituents are the wave energy production, tides and tidal energy production, parts of tidal energy plant, and then world and Indian tidal energy scenario. Okay. So it consists of the wave energies, uh, wave energy production, the tides and the tidal energies. Okay, different types of the tidal gates, tidal turbines, different types of the tidal turbines, horizontal axis and vertical axis turbines, tidal fences, tidal barrages, like that. So every details of the constituents, components of the tidal energy generation. Okay. So now coming to the question that the environmental impact of the geothermal energies is, you can see that it actually incorporates basically a power plant, like, right. So the uh, major pollution it actually causes via air pollution and water pollution. Okay. So what is that thing that there are also some hazardous waste is actually generated from this particular geothermal energy. Okay, so this disposal of this particular hazardous waste into the water and all, this causes an overall water pollution. And even in the gaseous phase also, the disposal on the emitting of this particular gaseous component also there are, like sulfur based materials, okay, carbon based materials, they ammonia, methane, okay, H2S, these actually are generated by this steam generator. Okay, and due to that, this particular environmental, there is certain environmental impact is there. It's not as green as the direct solar energy and the wind energies. Okay. Further, what happens is that there are certain dissolved solids are also there. Okay, so these dissolved solids, what they actually consist of, this consist of the chlorides, sulfurs, silica components, different metals also even. Okay, so these toxic heavy metals again, it they get into the water and then they discharge into the waters. So again they causes the water pollution. So in that way, the environmentally it can impact. Okay, so coming to the different sample questions, the first question is that which of the following statement is valid for a run of river hydropower scheme? Powerhouse is located along the main course of the river, normal flow of the river is not materially disturbed due to the construction of the plant, do not substantially alter the regime of the river, or all of the above. Yeah, so correct. It's all of the above because of run of a river scheme. If you see, it's basically a normal flow of the river is not materially disturbed due to construction of the plant. So it's constructed by the banks of the river. uh, it neither have a large reservoir nor do they have a diversion of the water away from the main channel. Already told, there is nothing like diversion or disturbance to the original river, so not hampering the original course of the river channel. Okay, so again the powerhouse is located along the main course of the river, is located along the banks. Okay, do not substantially alter the regime of the river. Same things. Generally, medium have high head installations, small pools or reservoirs to provide the necessary pondage in order to balance day-to-day fluctuations. So very small reservoirs are actually provided in because day to day there is some fluctuations to balance that, to generate the same amount of electricity. So kind of a backup system is there. Okay. and usually a very quite popular thing in Europe and hilly regions of India, because high velocity or high flow rate of the river is actually obtained in the hilly regions. In turbo turbine, the jet strikes the plane of the runner at an angle of 20 to 25 degrees, 5 to 10 degrees, 30 to 45 degrees, or 10 to 15 degrees. So the correct answer is 20 to 25 degrees. So you can see the different turbines as I already told. One example is Pelton turbine. It's basically consists of a wheel with a series of split buckets set around its rim. So this kind of bucket type thing is actually set around its rim, and a high velocity jet of water is directed tangentially at the wheel in the tangent form, directed at the wheel, and the jet hits each bucket and is split in half, so that each half is turned and deflected back almost through 180 degree. Okay, so it's very similar to the Pelton turbine is a turbo turbine, but the thing is that there is a instead of a tangential water direction, the jet strikes the plane of the runner at an angle of about 20 to 25 degrees, so that the water enters the runner on one side and exit on the other. Okay, and a turbo turbine can have a smaller diameter runner and rotate faster than a Pelton. So this is the difference. So correct answer is 20 to 25 degrees. Next question is specific speed ns for a hydro turbine can be calculated using the formula. There are four options given. Ns equals to np to the power half divided by h to the power 5 by 4. Ns equals to np to the power 3 by 2 divided by h to the power 5 by 4. Np to the power 5 by 2 divided by h to the power half, and np to the power half divided by h to the power 5 by 2. And the correct answer is np to the power half divided by h to the power 5 by 4. You can see the specific speed ns is directly proportional to the turbine speed, proportional to the square root of rated power, and inversely proportional to the head to the power 5 by 4. Okay, and according to this particular formula, you can see that the different types of runners, which means the Pelton having a 12 to 30 specific speed, Targo having a 20 to 70, cross flow having 20 to 80, specific speed, Francis having 80 to 400, and propeller and Kaplan having the highest specific speed, which means the 340 to 1000 up to 1000. Okay, and which means that the specific speed is nothing but, you can see on the right also, it refers to the point of maximum efficiency. It is something which is given by the manufacturer, and ultimately in the regular case we will uh, get a lower speed anyway, because in nothing runs at the maximum efficiency. Next question is, uh, the diameter increases in the flow direction. These things happen for what? Guide vanes, penstock, draft tube, or none of the above. Okay, so correct answer is the draft tube. So for a draft tube, you can see its diameter actually increases in the flow direction. So it's nothing but a gradually expanding tube which discharges water passing through the runner to tail race. Okay. On the contrary, what is a runner? Runner is nothing but the rotating part. The runner rotates due to impulse and reaction effects. It is made of cast iron, stainless steel, or bronze. The guide vanes are nothing but aerofoil shaped vanes fixed between two rings, and they convert a part of a pressure energy into kinetic energy. Then that thing comes into the runner like that. Tsunamis can be caused by earthquake, landslides, volcanic eruption, or all of the above. So the correct answer is all of the above. Okay. So like this hazardous wave, nothing but tsunamis are called. So this kind of hazardous wave can be caused by underwater disturbances that displace large amounts of water quickly, and it includes earthquakes, landslides, volcanic eruptions, all of these things. Waves caused by the gravitational interactions between the sun, moon, and the earth are called hurricane, typhoon, tidal waves, or none of the above. Okay. So the correct answer is the tidal waves. So the tides are nothing but a periodic rise and fall of the sea surface, which happens once or twice in a day, and this is driven by gravitational attraction by sun and moon and earth's rotation. Okay, so tidal waves are actually caused by the interaction between sun, moon, and earth. So there are uh, certain times, such as high spring tides occurs when sun and the moon lines up with the earth. This occurs whether they are either on the same or opposite side. Okay, and low neap tides occur when the sun and moon line up at 90 degrees to each other. There are other examples such as flood currents, ebb currents, like that. Which one is not related to hydromechanical equipment? Transformer, speed increaser, turbine, or gate? Which one is not related to hydromechanical equipment? Transformer, speed increaser, turbine, or gate? No. Actually, the correct answer is the transformer. So, the hydromechanical equipment involves turbine, gate, valve, and speed increaser. It doesn't involve the transformer. Transformer is a part of the electrical equipment. Right. Other other electrical equipments are generators, controls and protection, transmission and distribution, like that. Next question is, routes for the direct application of geothermal energy is raising plants in greenhouses, heating water at the fish farm, hot springs, or all of the above. So the correct answer is the all of the above. Okay. So the direct exploitation of geothermal energy involves providing heat for buildings, hot spring used as spas, heating water as fish farms, providing heat to industrial processes, raising plants in greenhouses, and drying crops. And the indirect exploitation involves only the electricity generation and heat recovery. One example problem is, for a typical small hydro system, water flows through a head of 2.5 meters and a turbine that could take a maximum flow rate of 3 meter cube per second. So if the turbine efficiency 85%, drive efficiency 95%, generator efficiency 93%, the calculate the actual power generated in the hydro plant. So taking no more time, showing you the solution. So the overall system efficiency you can get by multiplying the individual efficiency as I told earlier. So it 0.85, 0.95, 0.93 multiplied is coming around 75.1%. Now putting the other values, we will get the maximum power output of the system. What is that? Is rho g h, okay, and it multiplied by head. So rho g q h. Rho is for water is nothing but 1000. So 1000 into head is flow rate is the 3, head is the 2.5, and g 10.81. You'll getting 73.575 kilowatt. Now efficiency is 75.1%. You need to just multiply the maximum power output into system efficiency. So that will be the actual power generated in the hydropower plant. Okay, simple problem. Another problem is a power plant turbine generator gearbox having 90, 95 and 97% efficiencies respectively. So the hydropower plant efficiency is, I've already told this, will be nothing, just need to multiply the individual component efficiencies. So 0.9, 0.95, 0.97 will multiply, you'll get 82.93%. In hydropower plants, energy produced by potential energy stored in water at heights, kinetic energy of water to turn the turbines, sound energy to rotate the generators, both A and B. So the correct answer is both A and B. So potential energy stored in water at heights and the kinetic energy of the water to turn the turbine. So both this kind of uh, energy is used to produce the particular energy which is generated in the hydropower plant. Okay, so how it happens is the hydropower plants capture the energy of falling water to generate electricity. Okay, and then the turbine converts the kinetic energy into mechanical energy. So obviously a falling water means it has a certain height, it has a certain velocity. So a certain height means it has a potential energy, it has a velocity, it means it has a kinetic energy. So the combination of these particular energies are important for this hydropower plant energy generation. Which of the following is an example of a reaction turbine? Kaplan turbine, Francis turbine, both A and B, and none of the above. Yeah, yes, you are correct. Both A and B, Kaplan and Francis turbine, are the examples of the reaction turbines, and it's nothing but reaction turbine. The water enters the runner partly with pressure energy and partly with a certain velocity head. Okay, so in this particular turbine, the runner blades rotates with respect to the guide vane opening. Okay, and a sudden decrease of the load takes place. The guide vane limits the decreases of the water flow. So the more or less the reaction turbines are actually used in a low and medium head, not for a very high head application. So what causes some rock to melt and solid metal to behave plastically in Earth's interior? High temperature and low pressure, low temperature and high pressure, high temperature and high pressure, and low temperature and low pressure. Correct answer is high temperature and high pressure. It is very obvious that in this inside of this particular Earth's crust, the temperature and pressure is very high, and due to the synergy of these two particular operating parameters, the some rocks gets melted and solid metal to behave plastically, and the actually Obviously, inside this kind of depth, the pressure is automatically very high. You can see that about 6,400 kilometer of height is there. If you get the rho gh is the pressure, so rho and g if it constant, so due to this h there will be high pressure, and the temperature is also shown in this particular picture is as high as a 5,000 degrees Celsius. So this particular geothermal gradient which is there from the surface to the interior, this is actually drives a continuous conduction of the thermal energy in the form of heat from the core to surface. So, and this particular high temperature and pressure in this Earth's interior cause some rock to melt and solid mantle to behave plastically, resulting in portions of the mantle convecting upwards since it is lighter than the surrounding rock. Which of the following statement is false for tidal energy? Surface waves are created by the friction between wind and surface water. Kinetic energy of waves and tides cannot be converted to usable form of energy. Hazardous waves called tsunamis can be caused by underwater disturbances such as earthquakes, landslides. The gravitational pull of the sun and moon on the earth can cause waves. So the correct answer is kinetic energy of waves and tides cannot be converted to the usable form of energy. Obviously, this is a false statement because this is actually happens. The kinetic energy of the waves and tides is actually converted to the usable form of energy, which is nothing but in the form of electricity. Okay. Which of the following properties corresponds to shoreline devices? They are situated at around 20-meter water depth. They are situated at more than 30-meter water depth. They do not require significant coastal earthworks. They are fixed to or embedded in the shoreline. Yeah. So they are fixed to or embedded in the shoreline. So these are the different shoreline devices. The shoreline, what are these? They are wave energy devices, which are basically, this is the nothing but the definition that the both in and out of the water, these are actually fixed to. Okay. The near shore devices, what are there? They are at about 20-meter water depth, and the offshore devices about at more than 30 meters. So the first thing is the example of the near shore device. The second one is the offshore device, and the one last one is the shoreline devices. Okay. Tidal turbines use similar technology to wind turbines, although their blades are much dash and dash. Shorter and stronger, longer and weaker, shorter and weaker, longer and stronger. Yeah. So shorter and stronger are the correct answer. So the tidal turbines are basically nothing but using a similar technology like wind turbines, and they are shorter but stronger because more and more current is there. So these water currents actually turn the turbine, and which in turn activates a generator that produces the electricity. You can see these are connected, and whatever energy is actually uh, generated passed through them. Okay. So very strong tidal zones such as Norwegian and British coastlines, this kind of systems work best. A general knowledge kind of question. The world's largest tidal powered installation is, some answers are there, and the correct answer is the Siwa Lake Tidal Power Station and South Korea, having a 254 megawatt of capacity. Is the world's largest tidal power installation. Its mean operating tidal range is about 5.6 meters with a spring tidal range of about 7.8 meters. The tidal range of a bay could approach 17 meters in extremity. About 110 billion tons of water flow into and out of the bay in one cycle. Calculate the total potential tidal energy of the bay in this extreme case in 1 year by using bidirectional turbines. So the number of tidal cycles you can just determine. It's about 24 hour multiplied by 365, and there is this particular factor is divided by 12.4. It comes around 706.5, and the number of times for the tide to drive the turbines is it's nothing but 2 cycles. Okay, so it comes around 1413, and then the total tidal energy is nothing but the this particular tidal time multiplied by the energy is mgh divided by 2. Okay, just put the values and get about 3.6 into 10 to the power 12 kilowatt hour. A turbine develops 9000 kilowatt when running at a speed of 140 rpm and under a head of 30 meters. Determine the specific speed. So you have given the particular values, the shaft power, turbine speed, head, all these things. Put these values in this particular formula, which is already discussed. The specific speed is nothing but n square root of p divided by h to the power 5 by 4. So n is 140, power is 9000 to the power half, and divided by head is 30 to the power 5 by 4. Comes around 189.16 rpm. So if the tidal range of tide at particular place is about 10 meters, calculate the potential energy content of the water in the basin at high tide if the tidal power plant has a surface area of 9 kilometers square. Surface density you have to assume about 1025.18 kg per meter cube. Okay. So you've been given this particular values. The rho is 1025 kg per meter cube, and there is a g is 9.81. Okay, so you can see the also the tidal range is given is about 10 meter. The surface of the tidal surface area is 9 kilometers square. The specific density is given. Okay, so to put these values for determination of the mass is nothing but volume into specific gravity. Volume comes about area into tidal range. So area is about 9 kilometers square. To convert it to meter, 10 to the power 6 multiplication into 10 meter tidal range into density. So this comes the mass of the water, and then utilize. And another thing what I think yeah, the potential energy, so it's nothing but the mgh. So okay, so half into mgh you have to calculate. So half into area into density into g into tidal range square. Okay, so half into 9 into 10 to the power 6 meter square into 1025 kg per meter cube is the specific density, and the g into tidal range square is 4.5 into 10 to the power 12 joule. Okay, so that's all from my side, uh, and this is all for this particular 7th live interaction session. Thank you.